Okay, so the next interesting part in line integral, after you have done knowing about the conservative vector field and its special properties, and the next topic we want to learn about one theorem where it's very helpful to simplify your work. Okay, so now we want to know what is inside the Green's theorem. So this one still has to do with the line integral, but using this theorem, so your computation becomes more simpler. Okay, before we proceed further, there are some other terminologies that you need to know. Okay, so in order to use the Green's theorem, the condition to use the Green's theorem, you must have the you must have a curve where the curve must be a closed and simple. You have a closed curve and simple and must be positively oriented. So now we want to know what is the meaning of positively oriented, what is the meaning of simple and connected. Okay, so now what is a positively oriented boundary means that okay, positively oriented means that you have a closed curve and it must be counterclockwise direction. It is saying that if you are walking around a lake, this is you are walking around the lake, and you have to make sure the water is always on your left side. You have to make sure when you're walking or jogging along the lake, and you have to make sure that the water is always on your left hand side. Okay, so then we have a positively oriented curve, or so sometimes we see that the counterclockwise or anti-clockwise direction. Okay, so since you have a closed curve and at the same time you must have a region. Okay, so this one is a closed the region is bounded by the closed curve C. Closed curve C. And another condition is the region or the curve. It is called simple closed curve, where you have just like this shape, just whatever shape, as long as they don't cross themselves. So this is not simple, and this is simple. So just like this one. Okay. So this is the condition for you to apply the Green's theorem. Okay, now we want to know further about the Green's theorem. Let R be a plane region. Okay, R be a region with a positively oriented piecewise. What does it mean? Positively oriented means always point counterclockwise or anti-clockwise direction. So you have a closed curve. Okay, simple closed curve. And then the boundary of that curve is positively oriented, meaning that always point counterclockwise, in the direction of counterclockwise. And piecewise meaning that you can let's say you have a triangle. From how can you get triangle? From some line segment line, right? 1, 2 and 3. So this is called piecewise. So this is also closed curve. Piecewise and smooth. Okay, piecewise, smooth. And simple close, they don't cross themselves. And positively oriented. So if you want to apply the Green's theorem, so let's say your particle is moving along, starting at this point. So this is the starting point, and end up, because you have a closed curve and you end up on the same point but in the direction of anti-clockwise manner. So if you want to use the standard calculation of the line integral along the curve C, you got 3 curves here, C1 plus C2 plus C3. So your calculation should be, you have to provide 3 line integrals for specific C, C1, C2 and C3. But since now you can see that you have a closed, simply connected in anti-clockwise direction, so you can use the Green's theorem to simplify your work. Okay, so let's say the vector function given in general in a component form, so P, Q. Okay, so here for Green's, we only apply the 2D system. Okay, the 2D system means only I and J. Okay, so if you have I, J and K, we have another theorem that can be applied, but it's not Green. Green's only 2D and on XY plane, must be I and J only. Okay, so that is the condition for Green's. So now what is the Green's say? The Green's theorem means that the left side, it is the Green's theorem is the relationship, or it can relate the line integral. You can see on your left side is the line integral m dot dr. You can relate the line integral and the this one. Okay, so f dot dr is p dx q dy, and the line integral can be represented by the we call that this as a surface integral, where you will learn this in the next section, or I would say that the line integral, which is a single integration here, can be approximated by, or the value of this line integral is the same as the double integral. The double integral of, so what is this? Qx minus py. So this one is actually the 2D curl f, which means that what is the meaning of 2D curl f? You are given an f, but your f is only I and j. So when you do the curl of that particular function, vector function I and j, so you only have the k, right? You will get only the k. Okay, but it's okay. We just so we just take note that, so how can you get this? So this one is from 2D curl f, so it is a curl f but only I and j, and end up you only get this one, qx minus py. Okay, so qx minus py is inside the curl f. So now the formula, or I would say the Green's theorem, is the relationship between the line integral and the surface integral, or the line integral or single integration to the double integral dA. Okay, so what is the physical meaning or the interpretation of the result of the f dot dr for this particular curve, where your curve is counterclockwise direction, and then closed curve? Okay, so the small circle here means it is a closed curve. Sometimes you can see from other books they will put the arrow. So this one means the positively oriented, which is part of the condition to apply the Green's theorem. But sometimes they don't put, so meaning that, so then you have to take note that to apply the Green's theorem, you have to make sure that your closed curve is in the counterclockwise manner. Okay. Alright. So what is the interpretation of the line integral on the left side? It is actually the total rotation. Okay. Imagine you have the region. Okay. So the region R is bounded by the curve, the closed curve C, and the C in the anti-clockwise direction. So the f dot dr here is the total rotation of, okay, if f here, so let's say we assume that f here is a fluid flow, because we know that fluid flow is one of the vector function. Okay, so let's say f is a fluid flow. So what is the interpretation of the f dot dr here? This one is actually the total rotation of the fluid along the curve, only on the curve. Okay, because we have this only C here. We have only C here, so meaning that the line integral along the curve C is the total rotation of the fluid flow along the curve C, where that total rotation along the curve C is equal to the total rotation, this one. Okay, I highlight a different thing. So this one, So the right side here is the total rotation of the fluid flow inside the curve. So along the curve, and since the curve becomes the boundary of the region R, so meaning that the total rotation along the curve is equal to the total rotation inside the region R, or inside the curve C. So that is the physical meaning of the Green's theorem. Okay, and I would say this one is condition. So R must be 2D space, only I and J. Okay, it must be 2D space enclosed by the simple closed curve C and anti-clockwise direction. So that is the Green's theorem. Okay, the thing that you have to take note that R is the condition to apply the Green's theorem. R must be simply connected region and positively oriented boundary C. Okay, always point in the anti-clockwise direction. Okay, so this one is actually the simplified form of the f dot dr. Okay, p dx q dy. Sometimes we use this notation, and sometimes we use this. Both are the same. You can use both, meaning that you have a closed curve and anti-clockwise direction. Okay, so that is about the Green's theorem. So this is the physical meaning. So meaning that the line integral says that the total rotation along the curve C is equal to the total rotation inside the or in the region R. Okay. So now look at the example. So here we have, maybe for Greens I put this as example 1. Okay, so we want to evaluate the line integral. Okay, just look at the B using the Green's theorem. Okay, so that one is already in the f dot dr. So this is example 1. So we have x squared plus y squared dx plus 2xy dy. Sometimes since they give you in this form, then you have to know this one is p dx plus q dy. Okay, because after this you have to differentiate the p and the y, the p and the q respect to x or y. Then you have to know which one is p, which one is q. Okay, because using the formula you have the p dy, p y minus qx minus p y. Okay, so then you can say that the p is x squared plus y squared, and the q is 2xy. So using the formula of the Greens, you have to have differentiate p respect to y and differentiate q respect to x. Okay, differentiate partially. So py we got 2y, and qx you got 2y. Qx minus py. Okay, so now using the Green's theorem, we want to solve this. Okay, firstly you have because the question here is saying using Green's theorem, so meaning that now you want to check whether is it the requirement to use the Green's theorem is fulfilled, because we know that we must have the closed curve. Okay, the C given here must be closed curve and anti-clockwise direction. So now we want to sketch the C provided. So as given, C consists of the basically from the part of the parabolic curve, and also there are some line segments. So we draw the sketch the curve first. So you've got this y, x. Okay, so now we read one by one. From 0, 0, okay, consists of the arc of the parabolic from 0, 0 to 2, 4. So 0, 0 is here, 0, 0, and let's say, okay, I put 2, 4 here. 2, this is 2, 4, and this is 4. Okay, so the first C is that direction. Okay, 0, 0 to 4, and line segment 2, 4 to 0, 4. So we have this one. And then another line segment 0, 4, 0, 4 to 0, 0. So now we can see that it turned back to the initial point, so it is closed, and the direction is anti-clockwise. So that's why you can apply the Green's theorem here, because we have we can see the regions there, right? You can see the region there. Because you need to have the region, because next you have to apply the double integral. Where the double integral, you must know what is the shape of the region and what is the equation that related to the region that you have. Okay, so now using the Green's theorem, where we need to find the f dot dr along the curve C, and C is a closed curve anti-clockwise direction. Now using Green's theorem, we have to apply the double integral, where the formula is qx minus py dA over the region R. Now you got the region here in this particular shape. So we have the equation. So this is the equation, y equal to x squared. Okay, so now we plug in the qx minus py that you have. Qx 2y minus qx minus py 2y dA. And since your integral is 0, and you will get 0. Okay, it's just like a magic, right? So you don't need to do a lot of calculation, and you got 0. Actually, if you test for the conservative vector field, and I'm sure that you will get the curl f is 0, and based on the closed curve property of the conservative vector field, and you will get your line integral is 0. Okay, and this is using the Green's theorem. We can easily obtain the result. But if you look at the first instruction here, I ask you actually I can ask you to evaluate directly using the previous the standard calculation of the line integral, where you have to find the line integral for each curve. So you got 3 curve, right? The C1, C2. So you got here you got so this one C1, this one C2, and this one C3. So you will have to obtain 3 different line integral, where it is something wasting of your time, where actually it is provided in the notes. So for C1, where this one, so you have to find the because this is just 2D, you can just substitute the whether you want to transform them into x only x, or into the only y, and you will get the answer. Okay, and then C2, a line segment, or again you can convert into you can here you can on the C2 the equation is y equal to 4, then you can substitute when y is 4 dy is 0, and when you put into the p dx plus q dy, and you will get only this, and you will get this particular value. And on the C3, again the line segment, so we know this one is on the y-axis, so x equal to 0 and dx 0, and we substitute and you will get 0. Okay, so when you total up, you will get 0, where this one is a bit longer process. Okay, but you can see here, if we use the Green's theorem, so just a few minutes only. Okay, so that is the benefit of using the Green's theorem to simplify your work, as long as the condition are fulfilled. Okay, so the second one is obtained here. Okay, we got this. Okay, so next, on the next video will be on the next example.